Thank you, Gilfam. Hello and welcome. I hope everybody had a great lunch. So, yeah, my name is Peter. I work at Google, and I work on supporting some of the operating system teams working on projects like Pigweed and Fuchsia. But today, I'm going to be talking about the LLVM build. I actually became involved in LLVM circa around 2015, and a year later, when Fuchsia project really started taking off, I started thinking a lot about building the toolchain, assembling the whole toolchain, creating a toolchain distribution. And I was looking at a lot of different options, thinking about how do I automate this whole process, how do I script everything together, and I couldn't really come up with a good solution. And then in 2016, I've attended my first LLVM Dev meeting, and at the Dev meeting, I actually watched tutorial from Chris Bieneman, developing and shipping LLVM and Clang with CMake. And that was really great because Chris first really taught me a lot about how LLVM build works, but also suggested some interesting ideas, like instead of automating around the LLVM build, around CMake, what if we actually use CMake as a scripting language? And I thought this was a really interesting idea. So after his talk, I actually started talking to Chris. He actually shared a couple of his work in progress patches with me, which I took, developed, eventually those landed, and that really became the runtimes build we have today, which I'm one of the maintainers for. And so yeah, a huge thanks to Chris. What I'm going to be presenting today is basically just an updated version of his tutorial. And I also hope that this is going to be encouraging for all of you, especially the newcomers. If you're interested in build, it's one of the areas where we can always use more help. And I'm really hopeful that in 7 years or maybe even earlier, one of you is actually going to be standing here and giving a similar talk or an updated version. So when talking about the build, let's start with CMake. I hope that most of you actually know what CMake is, but just in case you don't, CMake is the tool we use in LLVM. The official definition is a cross-platform build generator tool. What this means is it's a tool that you use to describe your project, how to build it, and then CMake will generate build files for your chosen build tool, which can be Ninja, Make, it could be Visual Studio, Xcode. CMake actually supports a wide variety of build tools and IDEs. An important thing about CMake is also it's cross-platform. It has very few dependencies. Basically, its only dependency is the C++ compiler, which makes it, I think, a great fit for LLVM, because in LLVM, we try to support a wide variety of environments, platforms, and CMake does so as well. Also, the other reason why I think CMake is a great fit for LLVM is because over the last couple of years, CMake has really took off and became basically the most dominant or the default C++ compiler, C++ build system. And since we are working on a C++ compiler, or it's one of the big parts of the LLVM project, I think that makes CMake a great fit. So in the rest of this tutorial, I'm going to cover roughly these areas. First, we'll take a look at how to build projects and runtimes. And then we're going to amp it up a little bit and try and build entire tool chains. Then we're going to take a look at an aspect that many of you might be interested in, which is how to actually make my build go faster. And then finally, we'll end up with some next steps and Q&A. So let's start with building projects and runtimes. And at this point, most of you probably want to know, okay, how do I build LLVM? So all you really need are these 4 commands. Now there's a lot going on, so let's talk about this a little bit. So in CMake builds, we typically recognize a couple of different stages, which are shown here. The first command is really like covering 2 stages, is the configuration and generation stage. So in the configuration stage, CMake parses your CMake list files. It evaluates those, interprets those, and then it generates build files for your chosen, using your chosen generator for your chosen build system. Then you can build the project either using CMake or directly invoking your build system, run all the tests, and install what you've built if you want to create a distribution that you can ship. Now let's take a closer look at individual arguments that you would pass to CMake. Let's start with the first one, -s, that points to the source directory. You cannot point CMake at just any source directory. You always have to start at source root, or what CMake calls the project source root. And in LLVM, we actually have a couple of them, but the 2 that you really should be using are LLVM and runtimes. These are top-level entry points into the rest of the build. Now, in the past, it used to be possible to also just build individual projects separately. Like you can point CMake directed at Clang or libc++, but we've been slowly moving away from that and trying to reuse more code between these projects by creating these top-level entry points. I will touch on some of that later in the talk. So you choose LLVM or runtimes. The next argument you have to specify is your build directory. No specific requirements other than I would always recommend using clean directory. You can actually, one of the nice things about building with CMake and building with doing what is known as the out-of-tree build is that you can actually have multiple builds side by side with different configurations. You can have release mode, debug mode, and use those as needed. The next one is the generator you want to use. So in my case, I use Ninja, and that's what I would highly recommend, especially if you really care about performance, because in my experience, Ninja tends to be the fastest generator out there. Unfortunately, it's not the default, at least not yet. The default is going to be Make. So if you want a Ninja, you have to specify it explicitly. And then if you invoke CMake with the -- build option, it will just go on and build your project. But that's equivalent to just calling Ninja directly. So in practice, myself and I think most developers just run Ninja. Ninja also accepts arguments, which are the name of the targets that you want to build. You can do it like this. So in this case, I would first build everything that I've configured, and then I can run all the tests with check all, and then finally run installation. And final argument that we can pass to CMake, and the one that we'll spend the rest of the talk talking about are different arguments. There's only one argument that you really have to pass when building LLVM, and that's the build type. This is basically telling CMake, how do you want to build your project? Do you want to optimize for debugability or performance? CMake comes with some of the pre-configured options, like the release debug, release with debug info, and min size. And I also touch on which one I would recommend later in this talk. Now, if you just use that, if you just set the CMake build type, that's generally just build LLVM, but in practice, you probably want to build more. And the way you do this is through additional arguments. And the two of the most common ones are the LLVM enable projects. This is how we specify what projects to build, and enable runtimes. Now, you may be wondering, what's the difference between the two? Like, where should I use which one? So let's take a closer look. The enable projects controls which projects are built. These are things like typically tools, things like Clang, Clang Tools Extra, LLD. And these are built using your host compiler. So whatever compiler you tell CMake to use, that's how it's going to build these projects. Enable runtimes is identical, almost identical, with the main difference being that it's not going to build those using your host compiler. It's going to use the just build compiler. So if you enable Clang, it will first build Clang, and then it will use that just build Clang to build those runtimes. And this is really useful, really important when you're building runtime libraries that you want to use with the just build Clang, things like libc++ and compiler-RT. Now, what CMake is actually going to do under the hood when you use those arguments is going to look something like this. So it's going to first build all those tools, Clang tools, LLD in this case. Then it's going to spin up a separate CMake sub-build, and it's going to build compiler-RT built-ins. And then it's going to spin up yet another CMake sub-build and build the rest of the runtimes, like compiler-RT, libc++, whatever you configure. You may be wondering, like, why is it done this way? It's actually a good question. So let's take a closer look. Right now, we have a bit of a problem in that we have a cyclic dependency between compiler-RT and other runtimes. Specifically, compiler-RT ships with a lot of different runtimes, like sanitizers, profiling runtime. But the important one are compiler-RT built-ins. And these are used whenever LLVM has to generate an out call into one of the built-ins. It will pull it from the built-ins library. And that means if you want to build libunwind, libc++ ABI, libc++ as a shared library, you need to link against built-ins, assuming you want to use compiler-RT. But then compiler-RT as a project also contains other runtimes, things like sanitizers and profiling runtime. And those use things like libunwind, libc++ ABI, or libc++. So the question is, like, how do we build those when we have this cycle? And the way we do this is we treat built-ins specially. We basically allow the build system to build built-ins separately outside of compiler-RT. Once we finish doing that, we can then build all the remaining runtimes. And that's how we get around these cycle problems. The unfortunate downside is we have to run a separate build for built-ins. But I'm also hoping this is something we could address in the future, and I'll touch on that later. So when it comes to building runtimes, there are two main ways you can go about it. The first one is just what I showed you, runtimes build. You say LLVM enable runtimes, these runtimes you want to build, and then you let the LLVM build do everything for you, all the orchestration, like configure all these different sub-builds, pass the right arguments into them, drive them. You don't have to do anything else. The other option is you can do it yourself. You can just build them by either invoking CMake manually or maybe writing your own script. And that gives you more flexibility. But it also potentially requires more maintenance, especially as LLVM and LLVM's build system keeps on evolving. So it's always up to you to decide how you want to do it. But in case you want to go down the second route, this is roughly how you would go about it. So first, I need to build all my tools. So I will invoke CMake against the LLVM source tree, and I will build my tools, in this case, Clang tools, extra LLD. And then I'm going to build runtime. So I'm going to point CMake at the runtime source directory, and then I'm going to pass the enable runtimes and the list of all the runtimes I want to build. Now, in this case, this is not very useful because this second invocation, this CMake that is going to build, this CMake build is going to build runtimes is actually going to use the host compiler, which on Linux is typically going to be GCC or whatever is in your user bin. And you probably want to use the just build compiler. So to do that, you would do this. You would actually invoke CMake and then explicitly point it at the Clang that you just built in a previous invocation. Now, in practice, you probably want to pass more than just the C compiler, right? If you build all of LLVM with all the tools, you may also want to pass in things like the archiver, linker if you're going to use LLD. The list is actually pretty long, and this is what the runtimes build gives you. Like, it handles all that. It makes sure that all the tools that were built that are available are going to be automatically passed through. If you are scripting this yourself, you have to do it yourself. So that was for just the basics, building projects, building runtimes. Now, what if I want to build an entire toolchain distribution? How would I go about that? There are a couple of useful options that we have to support this scenario. The first one is called LLVM distribution components, which really controls which components you want to build and you want to install. Because when you are building a full toolchain, you probably don't want to include everything we have in LLVM. Like, LLVM is really a huge project. We have lots of tools. Most of those are actually not interesting or useful if you are building a full toolchain. Now, all LLVM-based tools, as well as many of the other projects like Clang and LLD, are what we call components, and these can be listed in LLVM distribution components. So the way you use it is like this. You just add the extra argument, dash the LLVM distribution components, and you list the ones that you're interested in this case, Clang and LLD. And then you have a special target, which we call distribution, which is going to build just those components. So in this case, just Clang and LLD. And then install distribution lets you install those. The other option that's closely related and also very useful if you are building a full toolchain is LLVM install toolchain only. And what this does is basically tells the build system to omit any tools that are only intended for development or testing purposes, because we have a lot of those. And in practice, you don't really want to ship those with your toolchain. For example, if you're shipping a toolchain to your customers. And this is just a simple flag that you just turn on. Now, if you look at this, the list of flags we have to pass is getting kind of long. And so just maintaining it, just always like passing it manually can get pretty tedious. And it's even worse if you want to everybody on the team to use the same invocation. So the question is, can we simplify this, or can we make it easier for developers? And one way you can do this, aside from just, again, using custom scripts, is the CMake cache. So first time you run CMake on a project, it will generate what we call the cache file. And this cache file is just a list of values that you can put in there, and then CMake will load that cache file on a subsequent invocation. So it's kind of like a way to preserve state between different CMake invocations. What CMake also lets you do is it actually lets you pre-populate that cache from a file on your disk. And it's actually something we use to create basically a pre-canned configurations. We actually have a couple of those. If you go to Clang CMake caches, there's lots of different examples, lots of complex configurations. But the way you're going to go about this is something like this. So this is an example where all those arguments I've used before, I would just put them into the CMake cache file, same exact values before, and then I can just invoke CMake just like before and point it at the cache file using the -c option. Now at this point, some of you may be wondering, what is this? So this is CMake, but this is CMake as a scripting language. And I've decided I'm going to try something, I'm not sure if it's possible, but I'll try to teach you CMake in a single slide. And now to set the expectations, I'm not going to teach you all of CMake because CMake is a huge language. It has a great documentation, there are books written about it. I'll just try to teach you what you need to know to write these cache files. And one of the things that I've noticed is very often when people teach CMake, they really approach it from first principles. But many of you are compiler engineers, language experts, and the thing that helped me to really understand CMake is to start thinking about CMake as TCL, also known as TCL. TCL only has really two principles. Everything in TCL is a command, and everything is a string. And the fact is, CMake is kind of actually the same. So in CMake, everything is a command that just takes a list of arguments, and every value is a string. And that's really all there is to CMake. You really don't need to know anything else. Now, to demonstrate this using some examples, let's set a variable. So in this case, we will set variable A, and the value is going to be string B space C. And then we can set variable D, and value is going to be what you see there. We can use the previously set variable in the subsequent commands. And what is interesting, if you pass multiple arguments that are separated by spaces, CMake automatically inserts semicolons, and it treats it as a list. So in CMake, there are no lists. Like I said, everything is a string. But there is a way to do lists as semicolon-separated strings. Now, I also said that every command just takes a list of arguments. So what I can actually do in this case, I can just expand the variable D and pass it directly to the set command. And now, question for all of you is, what is this going to print? One interesting thing about this example is, I'm not sure if you noticed this, but, well, actually, first of all, does anybody have any guesses? Yeah, EF, that's actually correct. And so what is going to happen is, actually, in this for each, what you can see, we will evaluate A, and that's going to evaluate into the string B and C. And then before, when we've expanded, when we set, when we pass the expansion of D, it actually uses A, or expansion of A, as the name of the variable, and then E and F as two values. And because they are space separated, it's going to become a list. Now, the interesting thing about this example is that we actually have a name. We have a variable whose name has a space in it. Is the variable B space C. And what is interesting is that you cannot actually write this in CMake. But if you use the expansion, CMake will totally let you do it. There are no constraints on what characters you can put into the variable name. And you will actually later see that there are cases where we use it or abuse it when we want to create kind of an object-style hierarchies in CMake, even though CMake really only recognizes strings. The other thing that you may have also noticed before, or you may have seen in our CMake files, is we sometimes have invocations like this, right? And it says bool. And so remember you wondering hey, Peter, you said there are only strings. What is this bool thing? So this bool, and you can also put string or path or file path, is just a type hint. And the only place where it's actually used is just in a CMake UI. So CMake actually comes with two different UIs, graphical and textual. And if you, for example, run the graphical, it's actually going to show these values. And if you put a bool in there, it will render it as a checkbox. But that's really the only use for the type. And as you can see, I can totally assign string into something that I say is bool, and CMake is just going to be fine with it, because in the end, everything is a string. Even something like a true or on is actually going to be a string. Which actually brings me to another example, right? CMake is kind of loose when it comes to booleans. So really, booleans is just a list of special values. It recognizes things like 1 and 0, on and off, true or false. Also, rules for evaluating variables are a little loose, which sometimes can catch people off guard. So here's another example. Actually, I've already shown you the answer. But yeah, the question is going to be, what is it going to print? And it's going to print off And the reason for that is in the if statement, we're going to first expand the variable y, and that's actually going to expand just to x. And now when CMake sees if x, it is actually going to take the name, it's going to treat x as the name of a variable. So it's going to then go on and internally evaluate x, which evaluates to off. And so that's why it's going to take that else branch. And I've actually seen, even I've made this mistake, when if you're not careful, this can actually introduce subtle bugs. So this is something to be aware of. So this is really all I have on CMake. This really should be enough to like let you write cache files, but there's a lot more. And one thing that I really like about CMake is actually it has pretty great documentation, great manuals. So if you want to learn more, I would highly encourage you to read those. But going back to the main talk, sometimes you want to do more complex scenarios, especially when building tool chains. A great example would be because I don't know what capabilities my host toolchain has. Maybe it's a host compiler, it could be GCC. I don't know if it supports things like LTO or PGO. I want to use those to build my toolchain. You may want to do things like multi-stage builds, where you first build toolchain once to set up your baseline, and then use the just build toolchain to build a toolchain again, and maybe do things like LTO and PGO optimization. This is actually something we also support in the Clang build. This is through the Clang enable bootstrap option, which is supported by two other variables. One of them is called the bootstrap pass-through, which lets you control which variables that you pass to CMake will get passed through to subsequent stages. And then Clang bootstrap targets will let you expose targets from those later stages at the top level build. So the way you would use this is something like this. You enable the bootstrapping just by saying Clang enable bootstrap on. Then I can say, OK, I want to pass the install prefix into the second stage. And then I want to expose the check all target from a second stage in the top level build. And so what I can do is I can then run Ninja and ask it to build stage 2, and that's actually going to automatically build stage 1 because that's a dependency of the stage 2 compiler, and then build stage 2 compiler with the first stage compiler. And then I can invoke check all because that's exposed. I just said I asked CMake to expose this with the Clang bootstrap targets command, and then if I say stage 2 install, it will actually use the prefix because that is being passed through. I can also cross-compile runtimes. And this is really important if you want to use Clang as a cross-compiler. So Clang and LLVM actually supports targeting multiple different architectures, different operating systems, one of the strengths of Clang and LLVM. But just building tools, the compiler itself is not enough. You also need other runtimes, things like compile-RT and libc++. And we can also build all those in a single build. And to do so, we have two variables. The first one is the LLVM built-in targets, and the second one is LLVM runtime targets. As the name suggests, the first one is used to build built-ins, the other one is used to build the other runtimes. And we also have a syntax that lets you pass variables into those different built-in builds and runtimes builds. To give you an example, so to build built-ins for two different targets, in this case, it's x86 Linux and AR64 Linux, I would just first set the LLVM built-in targets on the first line, and then I iterate over those, and I can set whatever variable I need. And here you can actually see I'm using this prefix in syntax, where I first use built-ins underscore, then it's going to be the name of target. So in this case, it's going to be either x86 Linux GNU or AR64 Linux GNU, and then underscore and the rest of the variable. And CMake will just slice it up and pass it into those sub-builds automatically. And also, here's an example how I can actually check if a variable was set, even inside a cache file, and if so, also pass it into one of these sub-builds. So to use this, here's the same thing for runtimes. It's identical, just a different name. And to use this, I would just invoke CMake, and then I can actually give it two arguments, pointed at the systree that I want to use. And then I can just run Ninja and build two of my targets. The first one is going to be the runtimes, x86 Linux GNU. The other one is going to be AR64 Linux GNU. And CMake is going to build all those automatically for me. There's also a limited or basic support for multilibs that we implemented, which lets you build runtimes multiple times for different variants. And what those variants do is basically up to you how you define those. We have the LLVM runtime multilibs that can be used to define these variants, and then we use LLVM runtime multilib targets to map those to different targets, and then we again have these pass-through syntax to pass variables to these different variant builds. It's worth pointing out, like I said, it's fairly basic. Right now, it only supports runtimes other than compiler RT. And the reason for that is because we don't currently have the necessary driver support to handle the compile RT ones, things like sanitizers, built-ins. This could be implemented. We just didn't really have time and resources to do it so far. So to use it, you would do something like this. I first say I want to build two different multilibs, in this case, ASEN and Hosek. I configure which targets I want to build those for. So I want to build the ASEN variant for x86 Linux and Hosek for AR64 Linux. And then I will iterate over the array of multilibs and then over the array of targets, and I will set the right prefix variable. Now, this is a little complicated. So if anybody has any questions, we can come back to this later. One thing that I also point out here is this is like one of the common tricks in CMake. So CMake doesn't really have anything like a dictionary or a map, but you can basically model that by using clever variable names. So in this case, I can just say sanitizer underscore ASEN, sanitizer underscore Hosek. That's my key, and I set it to value. And then when I'm using it, I can just double expand that name, and I'm treating it basically like a dictionary or map. Now, one thing that's also worth pointing out is if you do something like this, this example that I just showed you, it's going to create a lot of builds, a lot of sub-builds, right? Basically, for every one of, so first I have to build all my tools, then I have to build built-ins, then I have to build the main variant, then I have to build the multilib variant, then I have to build built-ins again for the different target, then rest of runtimes, and then the multilib variant again. So I'm going to end up with a lot of CMake builds that are all nested, they are waiting on each other. So the whole build is actually going to take a while. In Fuchsia, currently, our main tool chain, we build runtimes for, I think, 10 plus targets. And for many of those, we actually use 2 to 4 variants. And the build can be really, really expensive. Like, we actually spend more time building all the built-ins and runtimes for these different targets and different multiple variants than we actually spend time building the main tools. And so that's something to be aware of and be careful when you are deciding what combination of targets you want to build those runtimes for. And so speaking of speed, this is the part that many of you may have been waiting for. How do I make my build go faster? There are a couple of ways you can go about it. The first one I've already touched on is like with the build modes. CMake supports a couple of main build modes like release and debug. In my experience, unless you have some particular reason to use a debug build, like you want to actually load Clang or any other tools into a debugger and actually do interactive debugging, my recommendation would be just to use release mode. And in particular, I would actually recommend using release mode with assertions enabled. So normally assertions are only enabled in the debug mode, but in our experience for sort of day-to-day development, the best combination is release mode and then explicitly enable assertions because that still gives you compiler that's pretty fast, it builds fast, it doesn't produce a lot of extra data, like large build directories, but assertions can still catch a lot of basic issues. The other thing you can do is just use faster tools. I've already mentioned Ninja. This is an example of where just choosing the right generator can make your build go faster. But there are other things you can do. The most common one is the LLVM optimized table gen. So what this is going to do, actually similar to how we do these sub builds for different built-ins and runtimes, it is also going to spin up a separate CMake sub build to build table gen in a release mode with all optimizations enabled, regardless of where your main LLVM build is debug or release. And this is really important because we have lots of table gen files, and how fast table gen is really affects your build performance. So spending a little bit more time on optimizing table gen can really make a big difference. And that's why actually we have this option that does it for you. So my recommendation is always turn it on. 2 other flags, enable LLD and libcxx. This is only if your host compiler has those. But again, in our experience, LLD tends to be much faster than other linkers, and the same with libcxx or libc++ as the C++ standard library. The other thing that can also help is just optimizing your host compiler, especially if you're using Clang as your host compiler. Really turning on things like LTO, PGO, Bolt can make a huge difference. In our experience, it can make your build anywhere between 25 to 50% faster. And if you want to see how you can actually build an LTO, PG, and Bolt optimized builds of Clang toolchain, we actually have those examples. So all those techniques that I've just shown you with distribution, with multi-stage builds, distribution targets, we actually have examples that use all those and then do full LTO, full PGO, full Bolt builds. You will find it in the Clang CMake caches directory. I'm not going to show them here because I've actually tried in one of the earlier versions of the slides, and those cache files are so big that they are basically unreadable. So I would encourage you to just go and read them yourselves. Finally, you can also just build less code. And that's generally, like, I think, good advice. Like, that's always a good, like, an easy way to make your build go faster, just build less. And we've already seen some of the examples of how to build less. So if you can build fewer projects. If you don't care about some subprojects of LLVM, just don't put them into enable projects. Don't set enable projects equals all, because yeah, that's going to build everything, but it's also going to take a lot of time. Say with runtimes, or even with distribution components, like if you don't care about building all the tools, just don't do it. The other useful flag is the LLVM targets to build. That lets you exclude certain targets, certain backends. If you don't need them, if you, for example, only care about host, you can just put in native, and it's only going to build target for your host. And finally, you can try and leverage caching. It's actually pretty easy with CMake. There is a sort of built-in support into CMake through the CMake CNCXS compiler launcher flag. You can just point it at Ccache, the CC, and that tends to work reasonably well. It really depends on your use case, and that's why I said it can speed up your build, but not necessarily. It really depends whether you are doing clean build, increment the build, how much sharing there is between different build directories. So your experience with these might actually vary. So that was for building faster. These are the common tricks that I know and that I recommend to people. Let's now take a look at some of the potential improvements that I would actually like to see to make our build even better. And I've already touched on some of these throughout the talk. So first of all, like you've seen, right now we always spin up that separate build for built-ins. And that actually slows down the build and makes everything more complicated. And really, ideally, it shouldn't be necessary. Unfortunately, it is right now because we don't have the dependency set up correctly. So CMake and the generated build files don't really know how to order things correctly. But I really believe that it should be possible to make it so we can build everything in a single build if we do things right. But it's going to require a whole bunch of cleanup and refactoring to do so. But if we do it, we can really simplify and speed up the runtimes build, and I think that will help everybody. The other thing is, I would also like to build all the runtimes and runtimes build. Right now, it's a bit of a mix-up. For certain runtimes, like libc++, libc++, ABI, and libunwind, we only support runtimes build. For some of the others, like compile-RT or libc, we actually support multiple different ways of building those. So you can do them. You can build them in the runtimes build. You can build them as completely standalone projects. You can also build them as part of LLVM, and that complicates a build a lot because there are always free modes, lots of checking. We have to account for all the different options. Also, when we are doing cleanups, there's always something that breaks on some special configuration bot. So if you can just reduce the amount of options that we provide, the number of modes we support down to one, that would actually let us remove a lot of that complexity and simplify everything, and also potentially open new ways, new features, new ways of building things. I would also like to have a single top-level source tree. So right now, I said you have to pick whether you're going to start with LLVM or whether you're going to start with runtimes. But I really believe that developers shouldn't think about that, especially for newcomers. That makes LLVM kind of special and different from many, what I would consider idiomatic CMake projects. It's mostly a consequence of how LLVM sort of came to be, because in the past, before we were in monorepo, every subproject was its own subversion repo, so it made sense that everything was buildable separately. But now that everything lives in monorepo, I kind of wish that we would have a top-level CMake file that people can just point their build at, and then we will just figure out what to do based on the arguments. And I think we should also try and deduplicate and share common CMake modules across different projects, across different runtimes. Right now, we have a lot of duplication. We have a lot of modules that are duplicated between LLVM, between compile-RT, between with C++, and again, it just complicates maintenance. So there's a lot we can do. And finally, I would like to use more modern CMake. So CMake didn't always used to look like what I've shown. Actually, in the beginning, it was a much simpler language. It didn't even have a proper control flow. CMake really started adding a lot of support for actual scripting in the version 2. And really around the version 2.8 is where CMake really took off. And at that point, this is also where we started moving LLVM over to CMake. And so a lot of the concepts we have in our build date back to those days. But CMake kept on evolving. We are now in version 3.27. In LLVM, we use 3.20. But we haven't really started adopting some of the new concepts that CMake has. Like recent CMake versions have really doubled down on being more declarative, relying less on a global state, just following best practices that you will also see in many other build systems. And I think if we could adopt many of those principles, which sort of in general, like people refer to as modern CMake, I think it would make our build much, much nicer to work on, much simpler, and approachable to newcomers. And more generally, I think we should really be treating build like code, because it is code. It is code that keeps on evolving. There are people constantly bringing their own features, things they want to support. But in order to support those, we also need to dedicate time and resources to maintain that code, to maintain the build, do things like refactorings and cleanups. Otherwise, we're just going to keep on accumulating technical debt to the point when it becomes unsustainable. And so that's all I have for today. At this point, I would welcome any questions. And we have 2 mics over there.
Yeah. Thank you very much, Peter. Please come to the mics if you have any questions or comments.
So one of the problems you mentioned at the end about having a top-level CMake list file, right? So it feels to me nothing stopping us right now to doing that, right? So I've been doing that for a long time. Personally, I have my own top-level CMake list, that just creates a project, adds subdirectory to LLVM. Like mostly everything works. And if we did that, wouldn't break people going the old way, right? So like, why don't we just do it now, right?
It's just inertia and lack of, nobody was willing to put in the work. So I would actually encourage, if you have something that's working, just send out the PR and we can start having the discussion. I really think we should do it. So there's step 1, which is just to introduce the top-level CMake file. But I only think that's the beginning. I think what I would really like to get is to the point when we can then start looking at what are these common pieces across different subprojects, extracting those common modules. We have already introduced the top-level CMake directory where we've started moving some of the common pieces in there, but we haven't really gone as far as I would like to have.
Thanks for doing this talk. We do LLVM releases, and one thing that I realized recently from past couple of releases that our ARM build was not working just because of the problems that you have mentioned. So for newcomers, I recommend, for example, this talk is very beneficial for understanding the core problem that we have. And if we have a documentation of the problem somewhere, I'm sure there would be, but one of our engineers who started figuring things out, it took him a bit of time to understand the complexity of the build. So maybe if similar talks or maybe blogs or something in the LLVM wiki that we can have so that other people who might want to jump in quickly and help with fixing the overall or improving the overall. That's one comment.
Yeah, thank you for that suggestion. This is definitely something that I would actually acknowledge that I'm partially responsible for many of the fact that we don't have nearly enough documentation for some of the more advanced concepts like the runtimes build. Because as we are working on this, we are refactoring, nobody's really spending the time that's needed. But so there are some parts of the build that I think have pretty good documentation. We have 3 main pages that describe both the basics, like document different variables. We also have some sort of like a walkthrough of more advanced concepts, like talking about how to do like LTOP general builds. But I don't think it's enough. We definitely need to do better. I think one of the challenges that we have is also how do we make sure that the documentation stays up to date? Because we also have some documentation, even as I was preparing this talk, I've actually noticed some cases when I was reading the existing documentation where things are just no longer true or no longer valid. So we also need to spend time not just writing new documentation, but make sure that the documentation we already have is up to date.
Before this talk, I was not sure about the cyclic dependencies that you explained. So it was great that someone will watch your talk when it gets uploaded. I think it will provide a lot of information and knowledge around that area, because that is an important area of a complete toolchain build that we do within our company and within the upstream releases as well. So,
yeah.
Thanks.
Thank you.
Hi, so LLVM, in addition to CMake, has several alternative build systems. Off the top of my head, I'm aware that there's a Bazel build and a GN build. Could you comment on those?
Yeah, so we have, that's true. We have 2 other build systems in LLVM, GN and Bazel. Right now, those are supported and maintained on what I would consider best effort basis. So the idea is that if you are making changes to LLVM that could potentially break those builds, like you're adding new source files, or maybe you're modifying like build flags for existing source files, while we expect you, or like the contributors making those changes, to update necessary CMake files to make sure everything still builds, you're not required to go on and update those GN files or those Bazel files. There's a group of maintainers responsible for those build systems that do all that work. So at least right now, there's like no guarantee that those build systems are going to work. Most of the time they do, but it is not like the level of support is just different than what we provide for the CMake build.
Thanks.
So we found that performance where things should be parallelized is often not there for the runtimes build. For example, if you build multi-libs, each one is sequentially built one after the next rather than all in one go. We've looked a little bit at like the Ninja multi-build to fix that, but it looks like that's not applicable for the same sort of project in multiple configurations, because like CMake itself still has conflicts on variables. Do you have sort of thinking on this? One benefit of like having a separate runtime CMake list is you can just, well, okay, I give it a quarter of my cores and I do it 4 times, but if it's all together, it seems like it might become more.
Yeah, that's a great question, and something I've been thinking a lot about. So the first thing I'll mention, like the fact that like all these different subbuilds are serial, that's actually intentional, and the reason for that is console. Because every one of these subbuilds is still going to run CMake and it's going to run Ninja, and whenever something goes wrong, like there's a compilation error, we want developers to just see that right away. So that's why we've decided to give every one of these subbuilds direct access to console, but then console basically acts as as the resource that we contend on. So we can only have one build running at a time. We could, in theory, run these subbuilds in parallel if we were willing to redirect output, say, into a log file, and then that would help with the build performance, but it would probably regress the developer experience, because it means if one of these subbuilds fails, instead of seeing it directly in your terminal, you probably have to go and check out the file. One thing we could do is maybe expose this as an option, because especially like if you're building, say, on a bot, you don't really care about the interactive output. You may be actually totally fine just checking out the log, or maybe you can even have your bot just harvest all those logs and just expose them to users. So that's something we can look into. That would be fairly straightforward change. As far as other improvements go, I was actually experimenting a fair bit with the CMake, the multi-generator, which is a fairly new addition. So up until recently, we were still on CMake 3.13. That was the baseline we had for LLVM, which didn't have that support. I think the multi-generators were only to use in 3.15. But a few months ago, we bumped the minimum required version to 3.20. And so now that it is available, I would actually personally like to start taking advantage of that. One thing that I've been experimenting with is doing all of the multi-lib variants within a single build and just treat those as so the only thing that can, when you use the multi-generator, the only thing that can differ between those different builds is the build type, right? So like, for example, you can build both release and debug in a single build. You just end up with multiple Ninja files which then correctly reference each other. And so like one of the obvious ways that we could use it, we could use it for is to replace the sub build for the optimized table gen. So we can have the main build, even if you're doing debug, we can still spin up, like create the second configuration for the optimized table gen that's going to use release and still do it all within a single build. It's something we already discussed in the past. But the thing is, the CMake build type, even though CMake recognizes those 4 common ones, like the release, debug, release optimized for size, and release with debug info, that's just a string. You can actually put anything you want in there with some constraints. So I have a little example, like a demo that actually I have on GitHub that I can share if you'd be interested, when I've actually managed to build like n different variants for like a RISC-V bare metal toolchain when I've used like the build type to represent all those different variants, like different configurations like hard float, soft float. And I can do all of that within a single CMake and Ninja invocation, and it seems to be working really nicely. While doing that, I've also found a couple of issues that we will first need to sort out to actually like use this for the runtimes build. But I definitely think this is something we should pursue. It's just a matter of spending time and resources. But yeah, if you're interested, we should definitely chat because that's something I would like to pursue.
Any other questions? Okay, let's give a big round of applause to Peter. Thank you so much.